Okay, it's 1 minute past and looks like we have a good number of attendees. Welcome everyone, welcome to the webinar. This is the first in its series organized by Business Finland, the Finnish government innovation funding and foreign investment arm. My name is Petra Söderling and I'm stationed in the US with the specific task to help American companies discover research and business opportunities in Finland. Before we get down to business, a quick word on house rules today. We have about a 30-35 minute presentation during which you can type in questions in the chat box. Your questions will only be visible to the organizer, not to the other attendees. And at the end of the presentation, I will host a Q&A session with the speaker to answer your questions. You can type the question anonymously or leave your name and a company so we can follow up with you later if you have any additional questions. I'm not going to read out the name of your company or your name, just the question. Without further ado, let's get down to today's topic. I have an immense pleasure to introduce Antti Vasara, the CEO of VTT. He will have a slide in his presentation where he introduces himself in more detail, but I want to acknowledge he is much more than the sum of his resume. Mr. Vasara is a visionary and a deep thinker on technologies, research, and the role they play in societies, and I warmly recommend everyone follow him on social media. So go ahead, Antti, let's get started on quantum.
Thanks, Petra, and very good morning and good afternoon from me as well. It's 7 p.m. here in Finland, where I'm dialing in, and you can still enjoy the evening sun flowing in from the window. But let me now try to get the presentation up and running. Let me see.
It's coming up, yeah, looks good.
I hope you can see it perfectly. All right, okay. So today's topic is quantum technologies, but I wanted to use a few minutes first to introduce myself, but also then VTT, that who we are. A few words about me. So I've been CEO for VTT since 2015. I do have a background in physics. I got my PhD in photonics in 1991, but after that I went into the business world. So I worked for McKinsey for many years, then went to Nokia, and also been doing software and IT services in different companies. And also I've been seeing then the tech world as a non-executive director also in several listed companies. One was in Canada, one was in UK, and then several here in Finland. And in that sense, you could say that I've come back to my roots, coming back to a research institute, but it's also sort of then that the role that we have is to bring science, technology, people together then to solve those kinds of challenges that matter. And in terms of a little bit to kind of like open up the curtain that what VTT does, I want to share a brief video with you as an appetizer here in the beginning.
Wednesday, the day after Tuesday, not quite Thursday yet. And by the time the laundry's done, you can sense the world has spun just a little bit further beyond repair. What a time to be alive. Then again, this may be an ordinary day, but so was every day before every breakthrough. The day before we beat smallpox, before we saw an atom for the first time, the day before the first bytes of data shot across the World Wide Web. Never have futures unfolded in front of us as they do right now. As we speak, we are discovering extraordinary antimicrobial compounds in ordinary berries, so our children may beat superbacteria with cures directly from our forests. And right at this moment, we are designing hyperspectral cameras for satellites that let us see emissions and fight climate change from space. Plans are coming together for cities that are full of energy but free from pollution. So instead of cars, our children may focus on driving their dreams. We are living through pivotal moments every second. What an amazing time to be alive.
So the point with that is obviously that we are, of course, a research organization, the institute. We have lots of scientists in the company, and we do technologies. But there's a bigger purpose for what we're doing, and the idea is, of course, that we use science and technology as a tool then to bring solutions to the challenges that really matter to people and what makes them worried. And especially during the pandemic time, it sort of made our purpose even more visible in the sense then that all the research, all the R&D work, the innovation work that we do, unless it really answers those type of things that matter, it's all for nothing. And that's what we try to keep reminding ourselves, and that we need to be finding the best questions to solve, but also then that when we are trying to explain that why we are working on quantum technology or biotechnology or these types of things, then that there's always a purpose for that. And we are a government-owned organization, so we are fully owned. We are a limited liability company, but we're still owned by the Finnish Ministry of Economic Affairs and Employment, and they use as a tool then VTT then to help companies innovate, and that's then the role that we have, and that's why we are always eager to find ways how we can apply our competencies. Now today, and I could cover so many different topics about the research that we do, but today it's all about quantum. And the things that I hope that I can be covering today is obviously around why quantum is so exciting. And of course, I know that on the list of attendees there are people from many companies who are absolutely fantastic experts on quantum, so I can't teach you anything about quantum here. But for the people who are outside the field, I want to share first a few words about why this is so important. Quantum is the new transistor, so we are in front of a really big revolution in what we can do and what quantum will enable. This is the time to build the knowledge and expertise in quantum, so this is no longer sci-fi book stuff or sort of something that's only for the academia. This is really now the time to start building the expertise and start then applying it. So time to use that excellence is now, because the quantum industry is emerging, as we can see from the number of companies, from the funding rounds, but also then that the whole excitement around then that how close we are now then to start making actual real life applications around quantum as well. And I really want to be, for the people who are coming from outside the industry, I really want to be stressing this, that very seldom you can be at the junction that where you're really kind of like seeing something new and big emerge. But at the time that when it's happening, it's not necessarily self-evident that you are witnessing it. So I bet that the people who are inventing the first transistor in the 40s or the first integrated circuit in the 50s and still for many years after that, when it was in the labs, I'm sure they were excited about what they were working on, but they never would have been able to dream that what these two things, transistors and integrated circuits, have made possible in the past decades. So basically all the well-being and the prosperity that has been generated through different industries are one way or the other building on these two things. And I strongly believe then that quantum will do the same in the coming years and decades. Now, quantum is, of course, kind of like for the people who are in the industry, it's not the new thing. So, and already kind of like, even if you think about the applications, there are many quantum phenomena that are being applied in products today. So all the way from GPS and many types of electronic devices. But the way that we can now sort of really harness then the quantum state and start controlling at the level of single energy quanta means then that we can start applying it also as a compute. And of course the field is a lot wider than just quantum computing. We will see quantum communications, and many people talk about the applications around cybersecurity, which are extremely promising. Quantum sensing also will continue, and we will see more applications of that. But in the quantum computing, we are really talking also about the major breakthrough in terms of that we can finally bring something that goes way beyond Moore's law and what current computers can do. And in a way that you could say that although there will be still for many years to come huge advances coming on the classical computer side, we are seeing a plateauing that laws of physics are catching up with normal computers. So if we want to go significantly beyond them, we need something new, and that's where quantum computing comes in, and seeing then many orders of magnitude speed up then into what we can do with them. And that really is exciting. The application areas, and we could spend an hour just talking about these. So of course we can use a computer. Of course it can be applied in all areas, but there are of course areas where they are more applicable. And I'll come back to that in just one more slide. For the people outside the industry, why we are so excited about kind of like the classical versus quantum computers is then that the classical computers essentially are doing one thing at a time, and all the advances that we have seen in the past decades on that side have become through that we've been able to do that one operation faster and faster and faster and faster. And that's where the laws of nature are now catching up, that we can't make it go any faster anymore, even though that we're making them go parallel and all kinds of really cool things. In quantum computer, we're using the quantum state of some nanoscale structure, and with that quantum state, we can actually then, in a probabilistic way, calculate way more things in the same amount of time or energy, or whatever is the measure you want to use. And that way then achieve the so-called quantum supremacy, that we can do things with a quantum computer that are totally impossible on a classical computer. And there was roughly a year and a half ago or 2 years ago, when was it that Google announced that they have reached quantum supremacy around one particular algorithm, where the difference was between few hundred seconds and maybe it was few days on a classical computer, or many thousand years, depending on sort of how you see the situation, but still that the difference can be made incredibly big between classical computer and quantum computer. Now we do know that there are of course limitations to quantum computers, that there are certain type of algorithms or applications where we believe that we can achieve the quantum, or that at least it's possible to achieve quantum supremacy, and then some other areas where we at least at the moment do not know about algorithms that would make a huge difference. But even if it would be limited then to these few areas, then these can be absolutely crucial areas. So doing simulation of physical systems, so you can apply them into chemical reactions, biochemical things, biotechnology, these types of things, designing new pharmaceuticals or more energy efficient chemical processes. Factoring, which is the reason why people are excited about cybersecurity, doing certain type of math for artificial intelligence or deep learning, optimization, search, these types of things. So even if we will not see in the near future a general purpose quantum computer, if we can start building dedicated computers for these areas, we can do really interesting things with commercial and commercial application. So now, how do we then go about that? Why to even bother listening to what we are doing in Finland or Europe around this one? Firstly, I'm a strong believer in collaboration across borders, and also then that I've seen in my past life, for example, working for Nokia in the telecom industry, that how important it is then to accelerate the development of technologies by collaborating, even if you're then competing at the same time on then producing then the devices or products and then selling them to customers. So in certain ways, there are things that how we can speed up the development of technology and make things go faster. But there are also areas where I think that that still there are so many different technical questions to be solved that we need all the best brains in the world then to be solving these things, even if the companies are competing. First, a bit of a framing on the European scene. So everything that we do is of course built around then that we are looking for partners, and for us the natural place is then inside European Union then the large research programs that Europe is paying for. So Horizon 2020, which is the research program that's now ending this year, and then Horizon Europe that's starting next year. These are the biggest individual research funding programs that exist in the world, and always in there are certain programs that are chosen around key technologies where the basic idea is then that how we use that money then to bring different players together then to build these pre-competitive technologies together, so then that companies can use them then to build the actual products. And Quantum Flagship has been the key program around quantum technology in recent years, and hopefully will also continue in the future. But the idea there is that how do we utilize the scientific knowledge that we have in Europe and with partners all around the globe, then to start building both quantum communication infrastructure, but also quantum computing infrastructure, and move from the science phase then into the real business phase. The quantum industry is obviously emerging all around the world, and apologies that if this busy slide doesn't mention your company name, because it's probably already outdated. This is a really booming field, and we start also, of course, seeing then the kind of like the different segments around the enabling technologies. Where, for example, in Finland we have a company called Blueforce working on the dilution refrigerators. Companies building quantum computers. That where in Finland we have IQM. Building superconducting trans-quantum qubit-based computers, and then of course different type of software companies were developing then the different parts of the software stack that will be needed. And this is obviously one of the areas that which I will be also touching later on. My presentation will more focus on the hardware side, and that's mainly due to just our focus. But I do want to emphasize the need for the work on the quantum algorithm and software side, but also then that the even if companies are competing on developing qubits based on different types of physical phenomena and technologies, I think the area that where especially collaboration and standardization is important is that we start getting the software compatibility and open source software around then the quantum programming languages, so then that we can that way accelerate that how we get the technologies into use, but also then that we get interoperability as soon as possible. My background is in telecom, like Petra's as well, so we know that how important it is then to build that interoperability, because it basically builds a bigger cake, and that way makes the business boom a lot better than compared then to building these walled gardens and trying to kind of like build closed systems too early on. In Finland, as I mentioned, the focus has been coming from the hardware side, and the quantum technologies are emerging very much from the academia side. And you could say then that the history, why we have interest in the quantum technology, you could say that it's coming from the legacy, the heritage that we have around low temperature physics, and in a way that many of them, or most of the things that I will be talking today, you can trace them back then to the work that at one of the universities that nowadays called Aalto University here in the upper left corner. They had a low temperature lab that where they broke several world records in how close they could reach the absolute zero temperature. And that work then sparked a lot of technology development that we are now benefiting from. Also, the other area is then the kind of like that where the hardware knowledge has been cultivated is around the microelectronics ecosystem that we have been building. The centerpiece of that is a research facility called Micronode that we are operating here at VTT. And the basic background around that one is that when the world was going to CMOS technologies, and then in the microelectronics research that was done in the 90s, 80s and 90s, here in Finland, we saw that the CMOS investments were so huge that we wanted to pick a different focus, and we started researching technologies around silicon photonics, MEMS sensors, and actually also superconducting integrated circuits. So we thought that it's better than to pick certain clear focus areas and then start building competence around those. And now we've been working a lot then with different companies around there, developing techniques for artificial or augmented reality displays or different type of sensors and backplane components and these kinds of things. Now, this is then the basis also for the quantum ecosystem in Finland, in the sense then that we start now seeing then that the superconducting integrated circuit competence that we have fits perfectly into building quantum computers, at least certain type of quantum computers. The fundamental research and the low temperature work has then spun off these types of things like Blue Force, and then the work around the superconducting circuits have spun off then the IQM, which is then now building the first the quantum computers in Finland. And this is then the ecosystem that's building both in Finland, but also then all these parts are heavily linked then into the European part and working together in the larger context. What we then at VTT are working on in this, so that what's our part here is that, as I said, our history comes from the kind of like the quantum 1.0, so the quantum sensing, so doing squid-based magnetometer chips, superconducting multiplexers for example, satellite detector arrays, and then also doing bolometers for terahertz imaging, and that's been the kind of like the basis of the technology. But then when we realized that we actually have really good competencies around superconductive devices, we started moving then into the quantum part, and this is of course now then the one of the major assets that we hope to bring into this whole total picture. But also kind of like then the knowledge around MEMS sensors or photonics, for example, then as a potential way of then bringing the signal then to the cryostats are, so there are different types of elements that can be brought together. Now, as a research institute, also then that when we have been building our capabilities first on the kind of like you could say the traditional ICT side, but now also on the quantum side, now the bigger foundries and places that serve the semiconductor industry, they're usually gearing their operations towards performance and price, because basically the idea is that you need to go into fixed mass production and support that one. We as a research organization then that we have been able to focus just on the performance part. So our top 3 priorities are performance, but also then that we can support our customers in how to customize the solutions, to do smaller runs, but also then that how to work at the phase then that where the design is still changing, and that we believe is especially important for the quantum at the moment, because the design cycles need to be as fast as possible, but also kind of like then that how do you as the technology is developing so rapidly, that how do you turn the generations fast forward. We develop certain type of components also ourselves, so not only manufacture other people's designs, but we work on the kind of like the read-write circuitry for the quantum circuits, developing new types of ways how to do the cooling. For example, here in the middle, basically finding ways to kind of like skip the last coldest stage in the refrigeration process by utilizing certain type of electronic technology, and then these fast multi-channel qubit readouts for the qubits. Also, the other part where we're working a lot is then that how do we start scaling up when you go to error correction and these types of things. Currently, kind of like the designs are using the 2D lattices, where you also need to bring in the wiring in 2D, and that puts a limit then that how many qubits you can integrate then into one chip. But then if you put 3D integration, in the sense then that taking into account then that you can't kill the quantumness, you can't kill the quantum state by so how do we preserve then the quantum state, but then can do the auxiliary chips or the read-write wiring, doing the in multi-layer connections, and also then utilize then superconducting technologies then to kind of like bring the signal through the chip. So that's kind of like then one area that where we are developing technologies. These are all examples that where we are also kind of like part of then some of these European programs, like for example, this 3D integration is happening inside this open supercube, which is part of the quantum flagship. Then we also announced just before the summer that we will acquire and start operating then the first quantum computer in Finland, and the idea there is then that we want to really accelerate putting into use quantum computers because that we want to bring that close then to the company so that they can also start utilizing and testing and learning how to use them, but also then that we want to understand and learn more how to build the full quantum computer, and for that we open up the tendering process just before the summer, and it's underway, and the target there is that we will first build next year or get a 5-qubit computer, second phase 20 qubits, and then the third phase in perhaps 3 years time having 50 qubits. And that's also kind of like then that when we get to 50 qubits, then hopefully we've ourselves learned about how to build these quantum computers, but the idea is also that it serves as a open test bed then that other companies can bring their technologies. Maybe companies are building modules or components to quantum computers, so let's integrate them or software on top of it. So we are doing our best then to help that companies can utilize this also then to develop their own technologies that they are then selling then on the quantum field. So hopefully this will be kind of like one of the boosts that how we get the quantum industry going in our neck of the woods. How you work with VTT? So obviously, kind of like we are a research organization in the sense that we conduct research in these areas. So we work. It's normal thing for us that we work with customers and do contract research for them. We support companies with their manufacturing and pilot runs, so we can do the small volume and R&D manufacturing services, and we help then also companies then to take their designs then into large scale manufacturing. So how to then take it from these pilot runs then into full run. And we are totally used to working with companies also in the IPR matters. So the when companies are paying for the research, they also keep then the foreground IP. So I just want to finish here. I'm sure since you have dialed in, you share my enthusiasm for quantum technologies and the promise that it holds. And as Petra said, we are really much looking for partners in this area, both on the research side, but also on the manufacturing side. And as a result of my presentation, I hope, of course, that will get interested parties then to contact us so that we can get the experts to talk to each other, and we can start opening up ways how we can partner and do business together. And I bet that kind of like that in the coming years, people will be looking at the early qubits and kind of like wondering that how from these type of simple things, absolutely magnificent things came into fruition, and we will be creating something fantastic by doing this pioneering work at this point of time. So thanks for listening, and I think that we can now open up for the questions and Q&A.
Wonderful. Thank you so much, Antti. That was hugely interesting. I think you can unshare your screen so we don't look at your desktop. Thank you. So yeah, I have a number of questions here online, and I'm reading them in the order that they came in. And we're going to start with a really hard technical question that came in during when you were talking about the technologies in the quantum computing slide. And here's the question: how do we quantify certainty of an answer? Are Bayesian, with a capital B, are Bayesian techniques the best option?
Oh wow! now I have, I do have a PhD in physics, but kind of like that. Now you all immediately went beyond my understanding here. So I have to ask you then to send your contact information so that we can put you with the real experts and discuss with them.
Yeah, I think that's a good idea. A second question: are you talking to IBM on acquiring the quantum computer systems?
So we have a tendering process ongoing at the moment. Due to the, we're a government organization, there's a formal tendering process how it goes. I can't tell you at the moment who we are talking to while it's still ongoing. So I have to zip up here.
All right, makes sense. The follow-up question on the computer: if there's somebody who has a component and they still want to make an offer, is it possible to get, to still get shortlisted?
So we are buying the full system, but then the idea is that the system is open and we can continue working then with different types of players and kind of like continue improving it all the time. So I really would like to get you then in touch with us and continue the discussion. So I briefly showed the slide that where there was Himadri's name and email and contact information there. So please contact Himadri Majumdar, who's the program manager for our quantum computer.
Okay, and same type of question: if you're a software provider, do they need to work on specific application or use case, or because you mentioned chemistry, AI, you had a list of application areas?
So we are trying to be application agnostic at this stage, and because it's also then that we try to get as many companies as possible interested on working on top of that quantum computer. So that's why different application areas are really interesting. So please also be in touch there with us.
All right, question, actually they're coming in. So here's a question: one of the limiting factors in blockchain has been transaction speed. I do feel that with the new algorithms, quantum-based, this could be better. Would like to seek your view on this?
You mean that in
transaction speed? Well, in blockchain, the issue is transaction speed.
Yeah, so and not the issue with speeding up blockchain. So there are two ways how this question could be answered. Then that, or understood that can we speed up blockchain with this, or then that that's the problem with blockchain. So will that be also a problem with quantum computers in terms? So I don't know specifically about then that would this help with blockchain, but at least in terms of then that one of the issues, of course, with quantum computers at the moment is the how long we are still in the noisy intermediate phase here in the sort of how long algorithms we can run before basically the noise kills the process. So in that sense, then that I think that this is the area that we will see where we have to see improvement in the coming years. Then that we can run algorithms that produce a sort of a sensible or kind of like run an algorithm that is usable in for interesting problems. But at the moment, at the moment still, as I'm sure that you all know, then that there aren't very many useful things that you can do with the current stage quantum computers. But in a few years' time, I bet that situation will change.
Here's an interesting hardware question. Can you speak to future forms of peripherals and integrating with conventional computing networks?
So basically, one of the I think that one of the first applications of quantum computers will be that they will be quantum processing units, QPUs, that will be used kind of like you have GPUs or TensorFlow processing units at the moment in classical computers. So I think that that QPU is a very interesting route, and then kind of like the quantum unit will be performing a certain type of calculation, but all the other things will be done by the classical computer around that one. So in that sense, then that of course the integration will happen there. But if you're thinking about kind of like, can you get your Bluetooth keyboard hooked up then to that one, and I think that may not be relevant still for some years.
Yeah, I started thinking about like quantum refrigerators and toasters and things like this. So
yeah.
It would be an interesting idea. Question to VTT: where can I access an exec summary on what you're doing that I can share with my colleagues?
That's something, and we of course we can share this presentation, but also then that we'll provide a link on that one, then that where to find that. So our website is of course a good place, but again there, that kind of like that if you want more technical stuff, then again through Himadri you can get access then to the more technical specifications and descriptions that we have.
Yes, and I can answer from Business Finland's point of view. I'm here stationed in the US, and my job is specifically help American companies find the right people from VTT and other quantum organizations in Finland so we can do the matchmaking. Next question. In cybersecurity space, quantum computing changes the landscape. Will there be support programs for companies for readiness programs, such as shifting from non-compliant encryption to compliant?
That's an interesting question in a sense, then, that because of course the kind of like doing quantum proof encryption algorithms is a huge thing at the moment, and there's was it the DARPA competition that's ongoing in US as well, or sorry, I probably remember incorrectly who was the authority in US that is at the moment organizing the competition. I think there are now 15 competitors in the kind of in the next round. So I bet that's going to be an area then that where there will be a lot of competition, then that kind of like how do you roll it into use, and I hope that there will be a standard how that one will be done, like in the now RSA has been a de facto standard in encryption in the classical area. So kind of like then that we'll get the standard how to do quantum proof encryption.
Yeah,
I think we'll get support on that. That I think is companies who will do it. Then that, so it's for the IT consultants to do that.
And you have a program on security specifically. Is that something that American companies can join?
In Europe, you mean?
Yeah, if they want to, move to Espoo in Finland and join the security program that VTT is running.
So we are part of kind of like then the larger European programs that where we work. So there isn't a sort of a specific Finnish program on that one. So, but get interested then in the European bigger ones.
That's actually the next question. So how does what VTT is doing plugs into the flagship programs? You talked a little bit about that, but can you more specifically say if VTT has a certain role or a corner that you own and other people own other areas?
Yeah, so like how the European research programs usually work is then that there's a larger project that is done on a particular topic, and then a group of organizations gets chosen then to work on that one and get partially funded by the European Union, and partially they fund it themselves, and then they divide the work amongst themselves. So for example, in this open superQ that I mentioned, it's a larger program per se, and then we are working on the 3D integration part with certain competencies. So kind of like we are responsible for certain work packages, even though that the overall program is much larger. And then there are rules how the IPR is shared then among the participants, and how the information is shared, and those kinds of things. So it is of course sometimes a big work around those kinds of topics, but we pick certain topics that where we do then the contribution, and others work on other topics. And of course then that we can be doing our own research on a topic, and then once we have developed that, then we can use that then to be part of an European program then that where that contribution is then continued to be worked on.
Interesting. You mentioned IP. I just want to mention that in general, in Finland, the rules between research work done between companies and universities, the IP rules are more lax towards companies. So companies are able to keep a lot more IP than in some other regions. So that's a really good point to keep in mind. Next question. Do you generally agree with OIDA's published a roadmap in March and the Quantum Internet Initiative DOE released in July?
I'm afraid I don't know about those. So I confess that I haven't familiarized with those. So I don't know how to comment that.
Yes. Okay, that seems to be the last question from the audience today, unless someone is really quick. In the meanwhile, I still want to kind of highlight this. A lot is happening in Europe, and there's large budgets, public and private budgets, but a lot is happening in the US, both private and public, and even possibly a lot more than in Europe. So what would be a good incentive for American company to come to Finland and work with you on the quantum ecosystem?
Yeah, and of course we are extremely familiar with that, how large the US budget overall, and how the companies in US are investing into quantum. It's the same in Asia. If you look at what China and many of the countries they are doing, and then you look at tiny Finland, that okay, what can you do? But in a way that how technology gets developed, it's not linear in that way, that who has the biggest sack of money always gets the best results, because we are talking about technology that's in still very early stages, so that what are the winning constructions and technologies to be used is not all that clear. So in that sense then that it pays off to collaborate with even with your competitors then in developing some parts of the technology, and also then that you see that kind of like that since the field is also very vast, you can find companies and research institutes all over the world that happen to be in certain part extremely good. And since I have no part in Blue Force, I can brag about them. So for example, Blue Force has developed dilution refrigerators that are really crucial for at least certain type of quantum computers that are world's best. So that's a good example that you don't need billions of dollars in budget to be leading, so that you can find then different types of areas. And that's the basic idea then in very many technology fields, that why it pays off then to be looking around and kind of like seeing that what's also outside your own corner of the world, and finding then the best partnerships, how you can then then get competitive advantage.
Great answer. Thank you. Okay, we are running out of questions, so let's start wrapping up. If you have any more questions or you're interested in anything that Antti described today, you can send an email to me, first name dot last name at businessfinland.fi. So that's petra.soderling@businessfinland.fi. I also want to advertise our next webinars. We have a series, so we will be talking about artificial intelligence, cybersecurity, clean tech, autonomous vehicle R&D in Finland. So stay tuned for that. I want to thank our speaker today. Antti, thank you so much for making time in the evening. And I also want to thank our Business Finland coordinator, Ann Diskin in New York, who's been doing everything in the background. So big thanks and shout out to Ann. And thank you everyone for participating. This session has been recorded and we'll make the recording available to everyone. So with that, everyone have a really good day and good evening wherever you are.
Thank you. Bye-bye.